Thank you. Thank you, everyone. So my name is Minnie Park, and I'm a postdoc at Brookhaven National Laboratory. And today I'm presenting to give you an overview of the idealized cold air outbreak simulations that we have been working on recently. It's in a very at its like very infancy, but I'll go over their setup and present some very preliminary results. This work is through a collaboration with Adele Eigel from UC Davis, David from Activate Team, and finally Elsa Makomsky, who's now at NCAR. So as a refresher, because we've been hearing about all the measurements in the afternoon session so far, in wintertime, the Western North Atlantic presents the highest fraction of low clouds, primarily linked to the cold air outbreak events. As demonstrated in David's and Andrea's review papers, I took some of the figures from David's review paper here. Wintertime shows the highest surface fluxes, as you can see, the red shadings here, and cloud droplet number concentration here, despite the aerosol concentration and AOD being the minimum in the winter. So especially across the modeling team, at least 4 published work, to my knowledge, focus on cold air outbreak events. I listed the papers here and the dates and the grid resolution here and the model that they used. So they so like why we already have this 4 published works, so why are we doing another modeling study on wintertime marine cold air outbreak? So previous works have primarily focused on specific cases as listed in this middle column. Including the March 1st case, these are very valuable for providing detailed physical explanations alongside high resolution measurements made during the PIL campaign. On the other hand, the advantage of idealized simulations that we're to bring here lies in their ability to include or encompass a broader range of responses to various scenarios. So this approach, this idealized simulation approach, allows us to isolate and critically evaluate key physical processes free from the confounding factors typically present in more complex case studies. So to model marine cold air outbreak simulations, we adapted favorable synoptic conditions from the David's 2023 paper to set our initial conditions for simulations. As shown here, in David's paper, key synoptic conditions were identified using the self-organizing map. So the 15 patterns were identified and further categorized into 5 groups, as you can see from ridge, trough, and wake anomaly. So among the total of the 15 patterns, pattern number 3, which which is one of the trough category, is distinguished by the highest surface fluxes, as you can see here. And between 2018 and 2020, there are 17 dates that fall into this pattern, including the March 1st, 2020 case that analyzed by 3 published works within the Activate. So here, the overarching goal of this work is to investigate the individual and synergistic impacts of aerosol concentration that could serve as a CCN and sea surface fluxes on the properties of boundary layer clouds during the cold air outbreaks. And this goal is addressed by a suite of high resolution, meaning delta horizontal grid spacing of 100 meter, vertical grid spacing of 25 meter, and the model integration delta T is 1 second. So we use high resolution idealized cloud resolving modeling simulations by perturbing cloud CCN, sea surface temperature, and wind speed in the initial conditions. Here, the wind speed is marked gray as we haven't added any simulations yet for this factor. As such, the very preliminary results on perturbing CCN concentration and SST will be shown in the later slides. The model we use for our idealized simulations is open source regional atmosphere modeling system, RAMS, version 6.304. The domain is a single grid, non-rotating, with 2,000 points in the x-axis and 1,250 points in the y-axis, with the horizontal grid spacing of 100 meters to resolve large eddies. The vertical grid spacing is 25 meters, and we have 280 levels. Since we have a pre-described gradient in the sea surface to mimic the Gulf Stream in a highly idealized manner, boundary conditions were chosen accordingly. Each simulation runs for 15 hours, starting at 9 UTC with a 1 second time step. And for those who are more modeling savvy, here are some physics options that we use in this in our experiments here. And for the aerosols, we selected single mode ammonium sulfate for our simulations due to its widespread presence in the Western North Atlantic and its effectiveness as a cloud condensation nuclei, which can be attributed to its high solubility. And we have in RAMS, the RAMS has prognostic aerosol fields, and in the initial conditions, ammonium sulfate concentration is said to be exponentially decreasing with height, 200 at the surface in the control case. While we did not vary INP in this study, I'd like to open the floor for any insights at the end of the presentation on what might be considered reasonable INP values for this kind of environment. Any thoughts would be greatly appreciated. So it should be noted that in our idealized simulations, all simulations are initialized with the horizontally homogeneous thermodynamic and wind profiles. So as mentioned in the motivation slide, we use the average of, or we have 17 dates that are prone to have cold air outbreaks based on the BEAD's synoptic classification. And here for the simulation, we use the average of 17 trop days between 2018 and 2020 to represent the general environment for marine cold air outbreaks over the study region. So the three panels here describe how potential temperature, water vapor, and wind fields look from the average over the ocean-only domains. So in relation to the marine cold air outbreak index, which is often used to represent the occurrence or the intensity of the event, defined by the potential temperature difference between 800 hectopascal and sea surface. So in the base sounding, the potential temperature at 800 hectopascal is 293 Kelvin. And the schematic on here, on the right-hand side, illustrates how the sea surface gradient looks like in our simulations. The colder in the western 1/4 of the domain, and the warmer to its east. And as cold air outbreak occurs when cold air moves over to the warm ocean, wind blows from the west to the east in all simulations. So initial CCN concentration is one of the three factors that we perturb in our sensitivity experiments. While the control value of 200 is somewhat arbitrary, the range of CCN that we perturb in our experiments is bounded by Simon's 22 paper. So this is from his paper, all the BC, all from the below cloud-based, if I remember correctly. And if you look at this column, this is the CCN number concentration. And the red shading marks the highest value and the lowest value, and the average was 612. I think someone mentioned earlier today that we had more successful cold air outbreak flights in 2022. So I was wondering, does this mean the Activate team now has an updated range of CCNs during the winter? So anyway, the bottom line is that we, even though in its idealized simulations, we chose the range of CCN that we perturb based on the Activate measurements. The second factor we perturb is sea surface temperature. Again, this has important implications for changing sea surface temperature in a changing climate, and the marine cold air outbreak index changed by definition. So the left figure here shows the meridionally average sea surface temperature over this black box within our study domain for the 17 trop days. So based on this, we set our idealized SST gradient as shown on the right here, or this from the plan view. So to prevent any abrupt changes in SST and instead introduce a gradual increase in SST from the west to the east, we have this area where SST gradually increases with the slope of 0.08 Kelvin per kilometer, and this value is adapted from the previous study where the maximum value with the maximum value of the Gulf Stream SST gradient for the winter time was around this value. With that, here is an example plan view of control simulation. I'll just look through multiple times, but so here to describe the full evolution, I'm showing a loop from the beginning to the end of the 15-hour simulations. And the first two panels are vertical velocity and the total condensate mixing ratio around 1 kilometer model level. Oops. So on the first panel, which is the vertical velocity at the 1 kilometer, the red shading indicates the upward motion and the blue shading indicates the downward motion. And I'm not sure how well you could see from there, but I hope that you could see the juxtaposition of the red shadings and green shadings here, blue shadings, which means that the juxtaposition of the upward and downward motions repeatedly in the y directions. In other words, we see long rolls of counter-rotating air oriented approximately parallel to the ground in the boundary layer, namely, or in other words, the horizontal conductive rolls. And accordingly, if you look into the total condensate field at the same level, and also the liquid water path for the same simulation at the same time, we see the clouds forming with similar patterns to the vertical velocity. So the wind blows from the west to the east in the simulations, and you see the transition from the roll to cell structure from the west to the east as the simulation goes. And so as the analysis is still in its infancy, today I'll only go over changes in domain average cloud and drizzle mixing ratio. So here in this slide, this figure shows the control simulation with the lowest CCN and high SST here at the bottom right corner. So from here to its north, as you go up, initial CCN concentration increases from 200 to 500 and 1500. And if you go to the west, SST is decreasing by 4 Kelvin. Again, we have more simulations with more subtle changes in SST and CCN, but today I only show so-called extreme cases for the sake of time and simplicity. So in the control simulations, again, this is domain average, so x-axis is time and y-axis is height. So in the control simulations, at the first 3 hours of simulations, cloud mixing ratios increases with time, and after that, the domain mean cloud mixing ratio stays fairly constant. And if you go to this direction with more CCN, which is the difference between its sensitivity experiment and the control simulations, the positive value means that the more cloud mixing ratio in its simulations. So as you can see here, with more CCN, more massive clouds are observed, particularly above the 2 kilometer, as you can see in this red shadings, which is not surprising. and when you look into the changes or compare, or look into the figure here where the SST was decreased by 4 Kelvin, with colder SST, lower cloud mixing ratio values are observed in the entire cloud layer. And it makes sense given the critical role of surface fluxes in the cloud activation process and moisture availability determined or the moisture availability in the near surface. However, a detailed analysis of the microphysical process rates outputted in the RAMS model will be added to confirm or to come up with any explanations. And here is a similar figure, but for the drizzle mixing ratio. So the most distinct difference here is that the increasing CCN results in less domain mean drizzle mixing ratio in line with more cloud mixing ratio in the previous figure, whereas the colder SST results in less clouds and less drizzle mass. Again, this might be related to the role of surface fluxes and moisture availability in the near surface and boundary layer as a result of that. So again, like in today's updates, I barely touched the details or processes in each simulation. Instead, I intended to give you some general ideas of where our modeling experiment stands within the entire Activate modeling efforts. And I especially only presented how cloud and drizzle mixing ratio change as a function of changes in SST and CCN separately. Soon, the synergistic effects of both factors on the liquid hydrometeor distributions will be analyzed to be specific to see whether any interesting non-linearity or aerosol SST regime exists for this kind of environment. Yeah, that's all I have. But like finally, I just want to add that I'm transitioning from a BNL as a postdoc to NOAA Climate Prediction Center as a scientist position starting sometime in December. So I just want to thank Armin and the rest of the team for the great learning and research experiences during my postdoc, especially for introducing me, who was the deep convection person, who still is, to the boundary layer world. Despite my new role, I would like to finalize the analysis of the cold air outbreak simulations and submit it to a journal sometime next year. Thank you.
Okay, thanks, Minnie. Okay.
Hi, Minnie. This is Hailong. First of all, congratulations on your new position. And yeah, I was wondering when you you had a table listed all the CCN values. Are those at any supersaturation or?
I think it was at the 0.43%. I think Simone knows better. Yeah.
But your control simulation has the lower CCN number.
Yeah. Yeah.
So does that you use that to represent the average of those days you're simulating?
Not necessarily. I just wanted to start from somewhat lower end of the range and to increase it from there. Yeah.
I don't see a sorry, just minor questions. I don't see a size distribution you have here. What do you use for the average mean size in the model?
I don't have numbers here right now, but it's a single mode. Yeah, I need to look it up. But this, yeah, it's for the ammonium sulfate. I don't have the number right now, but I could look it up.
Okay.
Yeah.
All right. Thanks.
Thank you.
And Minnie, you mentioned something you heard, which we all heard too, that 2022 had the best colder outbreak cases. Can someone confirm here? Was that a data quality thing or more that we knew how to fly them better? I think it was the latter.
Yeah, I think it was the latter.
Did you have a question specifically about that? You said something about this table and if the numbers are still good or?
Yeah, or the do we have any like updated like stats for that the CCN number concentration with those flights included?
I don't think so. I haven't seen it, so. I mean, I don't think anyone's kind of put together a table like this for 2022, as far as I know. We could check with Simon's most recent paper, though. I don't know if this is his second or first paper here.
I think this was the first one, but I'll double check.
Okay.
Yeah, because this only includes the 2020 March and February flights. So.
Okay. All right, Ewan has a question.
Hey, the charts at the end that showed the time axis. Forgive me if this is a really dumb question, but so your domain has the spatial gradient, and you're feeding in air on the upwind side that has the kind of an initial state. So what is the significance of, what does it mean in the what's changing in time in that situation, right? Seems like it should be kind of stationary.
You mean, sorry, like in terms of clouds or?
Yeah, what is the significance of the time change that you're observing here?
Oh, I just like put it as there is like no significance in terms of like a time at here, but I just like first started with the whether there was any like changes in time, and the answer is like it doesn't look like there is a significance with the time. If I like average it with the time, that I would get the same results qualitatively.
So I guess the first 3 hours are is just the model spinning up, or is?
Yeah.
Okay.
From the very beginning of the simulation until it gets to the full structure, from the stationary and to the roll to cellular transition. Yeah.
Okay, and so the initial condition of the model is the same as what is the upwind boundary condition. Is that right, or?
Sorry.
Your westward boundary condition. Are you feeding constant air in from the left?
Oh.
Sorry.
Yeah. So.
Yeah, maybe
so
this is a rookie question.
No, it's okay. So maybe I didn't explain it. So in every grid point from the very beginning of the simulations, it starts with this condition. But because the general wind direction is from to the west to the east, the system moves like this way. But from every grid point from the very beginning of the simulation, it starts with this conditions. But we let the system evolve. Does it make sense?
Yeah, you don't have a research, but the air that's coming in the western side of your simulation has the properties you're showing in these charts, right?
Yeah, so I just want to give you the one because even though it's a horizontally homogeneous, the surface isn't, because it's colder in the western domain and it's warmer in the east.